Log on, tune in, find out. Another good idea from Cambridge.
Treespace with regard to many metrics that I think we've heard about recently.
Okay. So this is actually joint work with a team of 15 undergraduate students over the last 2.5 years. So 5 of them published a paper that is appearing this month in Information Processing Letters. So it's a program. So, and I'll show you a picture of a lot of them in the next slide. So I wanted to start by just saying what a phylogenetic tree is, and I will go quickly through this. So here's the part of Charles Darwin's diaries that was touring. I picked this up from American Museum of Natural History. And leaves represent extant species, as always, and turtle nodes represent extinct species, and if rooted, the root represents the ancestor of all species. When I'm thinking about trees, I'm not going to worry about the root. I'm sorry, I know people care. I'm not going to think about it. But what I am going to think about is actually searching for the best tree. And if you're interested in why we're searching for the best tree, well, we can think of this example. Oops. Back one more. This example from, if you visit the University of Texas and you walk into the biology building, there's this picture, 3 feet by 5 feet, with a little arrow saying, "You are here." So this is 5,000 species. I asked how they were chosen, and they were chosen by vote, how many grad students knew their name. Okay, so here's a tree. It's trying to represent the tree of life, but there's about 1.2 million known species, probably 10 million altogether. So one use for evolutionary trees obviously is to build the tree of life. You could also use it, and it is used for designing flu vaccines, other drugs, determining the origin of HIV drug. There's even an attempted murder trial, which it was used in. So here's some uses. Everyone's heard this, since this is a talk on phylogenetics. But I want to actually look at the space of trees. And so first I should actually talk about how many trees are there. And so it's a little hard to see, but here's the only tree shape on 3 taxa. There's only one possible. If you add a new one, you get 3 possible, because you add it in all places. And if you start adding more and more, it goes up by 5, and you end up with a lot. So I took this out of Mike and Charles's book, huge number. To make more sense of it, from 50 taxa, there are more tree topologies than there are atoms in the universe. Okay, so, and we're not interested in 50, we're interested in thousands of building our trees. So how do you find the best tree? Whatever method you use, most people have some optimality criteria, pick your favorite, and all the techniques, or the majority of the techniques, boil down to local search. What do I mean by local search? At each step you have a tree, maybe you run multiple chains, but you always have a tree, and from it you choose the next neighbor, and maybe you choose the best scoring one, maybe you roll a dice and you choose the best scoring one some of the time, but almost everyone uses a local search. But there's many different ways to define neighbors. And so this picture actually right here shows the trees for n equals 6. So if you did the math quickly, for 6 taxa, there's 105 trees. Okay, and these are actually organized by the NNI metric. So let me actually explain what different metrics are, and these are the different neighborhoods wandering out. We also have pictures for 7 and 8, but they don't look really good on the screen. So how do we define a neighborhood? I said we use a metric. So let me talk about 3 metrics, which people have talked a little bit about already. So the ones I'd like to talk about are nearest neighbor interchange, subtree, prune, and regraft, and tree bisection and reconnection. And I'd like to note, which was noted earlier, that every NNI move can be modeled by an SPR move, and every SPR move can be modeled by a TBR move. So NNI is the only one that really hasn't been defined yet in this talk, in this session. Everyone else has explained it. So what is NNI distance? NNI, let's start with an NNI move. An NNI move, you identify an edge. In this case, I chose the red edge between A, B, C, D, and E, F, G. And when you remove this edge, you split your tree into 4 subtrees. A, B, C, D, E, F, and F, G. You choose 2 of them and you flip their position. Okay, so this is one possible resulting tree, and if you play with it, you'll realize that there's only 3 possible trees. So the N and I distance is between 2 trees is the minimal number of N and I moves to transform one to the other. It's well defined, it is a distance, and like almost all distances except Robinson Pools, it is NP hard. Okay, this was shown in 97. Okay, SPR distance, which was also defined earlier. So this is the one where you prune a subtree. So let's say we take the subtree AB, we cut it, and we put it back somewhere else. Okay, and so the SPR distance is the minimal number of moves that transforms one tree into the other, minimal number of SPR moves. So SPR for rooted trees is NP hard due to Magnus and Charles, and for unrooted trees, it's also NP hard due to Hickey et al. Okay, so these are all hard, fortunately. And the last distance that I need is TBR. So TBR, I break some edge. Again, I'll use the same one I used before. And then I reconnect anywhere else in the tree. And it's, again, NP hard. So these are the 3 distances that people use to, usually very popular distances to explore tree space. I know there's others. I just want to talk about these guys. So let me say what I mean by a tree space. A tree space is the space of all phylogenetic trees on N taxa under a fixed metric. So here's a picture from Bastard et al. Of the N equal 5 tree space under N and I. Okay? Under N and I, you only have, when you have N equals 5, you only have one possible shape on the trees. So choose any tree and put it in the middle. And there's a line between any 2 trees if they're a single N and I move apart. Okay, so that's how they're being identified. So the size of the neighborhood, and in this case, if I focus on this center tree, it has 4 neighbors, 4 first neighbors. The size of the neighborhoods varies by metrics, and so this is from Allen and Steele, 2001. Here's the general bounds. For N and I, there's always exactly 2n minus 6 neighbors. And so in fact, if you think about N and I tree space as a graph, it's a k-regular graph where k equals 2n minus 6. So it has some actually interesting properties for that. So in this particular case, there's very few neighbors. There's only 4. For SPR, the number is 2 times n minus 3 times 2n minus 7. So in this case, this guy has 12 neighbors. That's right, yeah, because there's only 2 that are excluded. And it happens because the space is so small that the TBR neighborhood's the exact same size. As you get bigger, they split. And this is an upper bound on the TBR. The other 2 bounds are exact. Okay, so where am I going with this? I'm going to the first challenge on, don't worry, I didn't solve it. Okay. So we made partial progress on the combinatorial challenge of David, who came out fuzzy. Is he here? I don't see him here. He's fuzzy up here. Okay. So this is David Bryant, smiling. And here's his challenge. So his challenge is the first thing on the challenge list for this conference. And it was also a penny ante at several of the New Zealand phylogenetic meetings. So he says that he defines an NNI walk as a sequence of trees where each consecutive pair of trees differs by a single NNI move. So you're walking through tree space by NNI lengths. And so he asks 2 questions. The first question is, what is the shortest NNI walk that passes through all binary trees on N leaves? So take tree space. What's the shortest walk that visits every single tree? Okay, and he's doing it under NNI. And then the question that he was more interested in when I asked him is, suppose we're given a specific tree. What is the shortest NNI walk that passes through all trees that lie at most 1 SPR move from the tree T? So what is he saying here? Fix a tree T, look at its SPR neighborhood, and now we're using NNI moves. How long does it take to visit everything? So those are his conjectures. So the first thing I want to say is, for the simple case, this is our tree space again. Again, this is the picture from Bastert et al. Here is a path following only NNI links that visits them all. So there is actually a Hamiltonian path for n equals 5. So recall that a Hamiltonian path is a path that visits every node exactly once. So what we were actually able to show was that when you look at tree space under SPR and TBR metrics, so not under this NNI, but under SPR and TPR, we can find a Hamiltonian path. That is, the shortest path that visits every node is the right answer. Okay. For NNI, we were able to do it for n less than 7. Okay, and this is actually one of the amazing things about my undergraduate students, is that one of them wrote out all 945 7-leaf trees on separate pieces of paper. First, they covered every whiteboard in our office, or in our lab, I mean, and then they did it all on pieces of paper, and then they linked them together, covering every table they could. Okay, and they actually found me a path. Okay. There's also, and then a whole nother group is working on it computationally, just literally searching for all possible paths. Okay, so they have it for 7. So for 7, there's 945 trees. For 8, they're not there yet. There's 10,000 trees. Okay, so I'm hoping we're hoping working on to the next step of abstracting a little bit. Okay, so what's still open is what is the shortest path for NNI space for n greater than 8? And is there a better way to do it than writing out every single tree? So what can I tell you? On for SPR or TBR, so those are the ones where you're actually allowed to break an edge and reattach it somewhere else, you can get these Hamiltonian paths. And here's actually the idea. If I have a path for tree space on n, then I take every tree, so say this is a tree on size n, and I know that I can actually draw a path, a closed curve around this, okay? And I use that as my guide to have a path for the n plus 1 space. So that is, I expand the n tree into an m plus 1 tree, where I put into 2 times n minus 3 m plus 1 trees, where they are, you put the new leaf in any of the possible places, okay? And then for SPR and TBR, you can then walk around these new trees by just picking up the leaf and moving it. Okay, so it's very cute and it's very simple. And once you can show for n equals 5, you have one, you can have one in general. This isn't actually true for n and I, and you can see why. Is when you get to somewhere like right here, you can pick it up and move it here and here and here and here, but to come back up, you retrace a step. Okay, so the best we can actually do for n and I is that there's a 2 walk. So another explanation for another way to say Hamiltonian path is to say there's a 1 walk. You visit every node exactly once. And there's a general idea of a k walk where you visit everything at most k times. So you can get a 2 walk incredibly easily. So what do you do after you've done this for every single cluster of trees? Then you glue them together with the path you had from before, and that gives you your Hamiltonian path. So that was the first part of Bryant's conjecture. The second part of Bryant's conjecture, and as I said, it's still open. We just made some progress. What is the shortest NNI walk on an SPR neighborhood? So here's an SPR neighborhood. This is for n equals 6. This tree in the middle, marked 0, is a caterpillar. For n equals 6, there's actually only 2 different topologies possible. The caterpillar and what my students unfortunately were calling the stupid tree because it was annoying them. We're calling it the special tree currently. So here's the 0 node, okay? And this is its SPR neighborhood, okay? And it's colored by the NNI neighborhoods, how far out you're going. And so what we showed in this paper is that for n greater than or equal to 6, there are SPR neighborhoods, namely the neighborhood of the caterpillar, which don't have a Hamiltonian path. Okay? And if you look at this neighborhood, it's very clear that it doesn't have a Hamiltonian path. because of these isolated triangles, these triangles marked in blue. So any path that you start, let's say you start on this triangle, if you go up on one of these triangles, you have to come back down, so you don't get a Hamiltonian path. And what we can show is that for any length caterpillar, you get this shape, okay? And in fact, so that here's what I just said. The SPR neighborhood of caterpillars all have isolated triangles. So, okay. Oops. Okay, so here's actually n equals 7, the SPR neighborhood. And notice that we get these kind of tendrils coming out. And these correspond to taking the SPR move where you take, for example, the leaf N and you drag it to the other side and attach it by 1 or 2. And that's these right here. And this was, they were having fun with, these are all drawn in Cytoscape, which is used for drawing protein-protein interaction networks. It's an awesome visualization tool. They were having fun with the layout, but this is the other tree topology. Okay. So the shortest paths are +8 and +6 more than the minimal Hamiltonian path. And so they actually have some conjectures on how this actually grows. And I think I will, but they don't have any proofs yet, so I'm not going to say. But they're making progress, and it's a really interesting and fun question. So just to say what they did show and what's still open. So they can show that Treespace is Hamiltonian for SPR and TBR metrics, that it's Hamiltonian for small and less than 7 Treespaces under N and I. What's still open is what's the shortest path for N and I Treespace for N greater than or equal to 8. They can show that the minimal N and I walk of an SPR neighborhood is not Hamiltonian, but they don't know how long it is, how short it is for more than very small examples. So I keep talking about they. This is some of them, okay, over the last couple of years. And I'm doing for time. I'm doing great. Okay. So I wanted to thank the organizers and the Isaac Newton Institute, the U.S. National Science Foundation for all of their help, the Lewis Stokes Alliance for Minority Participation in Research for student funding, who have made it possible to have this many students floating around, and last but not least, my husband, Sean, who is single dad this week. So.
Heaps of time. Did you really get them to draw out all 905 trees and sort of circles and arrows? That would have been quite fun.
They work in
Get a
teams.
photograph of that as
I
well.
do. I actually sent that to my NSF director as my report. It was very pictured. Yeah, no, very proud of. Yeah.
What would happen if you went to rooted SPR and rooted NNI and things like that?
I'm kind of partial to unrooted.
Pardon?
I'm kind of partial to unrooted SPR. But what would happen to the neighborhoods? I don't know. I think the same things are going to occur. But I haven't thought about what happens with rooted. And I don't know which way David meant for it to be. It doesn't actually. I think it's unrooted, but he doesn't actually say on his space. I'm not sure.
Well, first of all, when you have 900 and however many cases, how many?
945.
945. How do you verify that what the students did was actually right?
I took 2 other teams of students and had them check. How's that?
No, that's absolutely.
No, but they have to come up with a more general way to do this. And then there's a group that's working, who's writing a computer program to search the spaces, and they were able to verify one of them.
The other comment is that this would be, for larger values, a great application of what's happening in a number of places in science. We're using social networks to just sort of broadcast problems and let thousands of people work on them, and like SETI at home and all of that.
Right, then you have to explain to all of them what a phylogenetic tree is.
Yeah, it would be a great way to involve outreach. That would be a good proposal.
Okay.
Andy?
You ever thought of a random NNI walk of a certain length and see what fraction of the SPR neighbors it picks up?
So they were trying random walks on the whole space, to see what they would get, and they end up getting about 70 to 75% of the tree space. A random walk with some backtracking. So I don't know what it does for the SPR. As I said, they have some conjectures for how it actually grows, but they weren't able to give me a convincing proof before I left. So I'm not gonna expand on it until I have a convincing proof.
All right. Oh, Vince.
Did you try any other visualizing any other metrics like quartet distance to see how the neighborhoods compare?
So we actually have visualizations of SPR, TBR, NNI, and a metric called rotation distance used in computer science. So we actually have tree spaces for that. That one's a little bit easier because the number of trees grows like the Catalan number, so it's smaller. But to actually do these visualizations, unfortunately, isn't that easy.
Was that really looking really quite different with the rotation distance? I mean, did it look...
Rotation distance looks it looks somewhat different. I mean, there's fewer trees, and rotation distance works on ordered trees where all the leaves are ordered left to right, 1 through n. The trees are rooted, and you basically can do n and i moves, but you have to keep the same order of the leaves. So the space does look different because there are many, many fewer trees, and you can't, move large distances.
I think we'll leave it there. Thank you very much.